So in this one, we'll take a look at catalysts. Catalysts are substances that change the speed of a chemical reaction without undergoing permanent change themselves. And it's one of the four ways that we can vary the kinetics or the speed of a reaction. Catalyst, temperature we looked at last time, the physical state of a reactant we'll look at the next video, and then lastly we'll look at a series of videos of how concentration can affect that. But right now we'll take a look at catalysts. Now there's two different kinds. There's homogeneous catalysts. Homogeneous catalysts are in the same phase of matter as the reactants. And then there are heterogeneous catalysts, and heterogeneous catalysts just being the opposite. They're in a different phase than the reactant. And the way that catalysts work is by taking and giving the reaction pathway an alternate path and lowering that activation energy. So you can see in this diagram right here that we have a red reaction pathway right here called the uncatalyzed reaction, and the E sub A would be from here to the very tip top of the red. And then there's a blue version right here that's a catalyzed reaction that happens to have two steps and an intermediate right here, and those have lower activation energy. So the overall activation energy then would be lower right here because it's symbolized by the lowest of the two bumps right, or the highest of the two bumps right here. But it would speed up the reaction by offering that alternate pathway. So here's the diagram I should draw right here. It offers an alternate pathway to lower the activation energy, and then you can write this as the uncatalyzed reaction. And then the catalyzed reaction, you could use a different color like they used here, or you could just draw it in maybe with little dashes, and you could show an alternate pathway. And the trick to drawing the alternate pathway is that the activation energy hill has to be lower, but it still has to start at the same energy and end at the same energy. So our overall delta H right here, or our overall enthalpy, remains the same, but the activation energy hill right here is lower. So it's offering an alternate pathway that lowers the E sub A, and therefore the reaction is faster. Well, let's get two examples of these catalyzed reactions, and the first one that probably comes to everybody's mind is something called a catalytic converter that is inside your car. So a catalytic converter takes exhaust gases, which generally have some nasty things in them, like nitrous oxides. We'll put NOx right here, because it could be NO, NO2, N2O, which we'll look at in just a second, are not nearly healthy for humans. They come from the engine right here. It also has carbon monoxide in there. It has some unreacted hydrocarbons, so CXHYs. And it puts them across a surface, and the surface is heterogeneous, obviously, because these are gases. They're really hot. And this surface is made of a precious metal like platinum or palladium or rhodium. And it allows these chemicals that we don't really like to adsorb, to stick to this surface. It has a hole right here in it, or an area where extra oxygen from the atmosphere can come in, and then it's like part of this molecule sticks to this surface, the other part can be pulled away, react with the extra oxygen, and then we can get two nitrogens to come together to make N2, and we can get extra oxygen here to go with those O's, and it'll give harmless nitrogen and oxygen aside. So let's take a look at a couple of slides or a couple of diagrams of this, and I've just got to click out of this. And then here is a couple of nitrogen oxide molecules that are not so good for you that come out of the emissions from the exhaust of a hydrocarbon-based engine. Long-term exposure can decrease lung function, increase the risk of respiratory conditions, and increase the response to allergens. So nitrous oxides right here also contribute to the formation of particles on ground level that include ozone, which is associated with health effects. So here is a diagram of an actual catalytic converter, and then you can see these are the exhaust gases right here. And you can see it's kind of a honeycomb shape inside of the catalytic converter. And that's so then no matter which way the air particles come in, they have a top, a bottom, and a side that they can bump into, because we want them to adsorb, the fancy name for stick to, some of the surface, and then they can react. And it's kind of small right here, but you can see some of these reactions make CO2, make H2O, make N2, and so it becomes less harmful. Here's a really nice kids diagram. And so here are the nitrous oxides, the carbon monoxide, and the CXHYs coming in. And then there's a couple of ceramic blocks right here that have those platinum, palladiums in it, and then you get these pieces out. And as you learned back in Chapter 4, these are reactions that are oxidation-reduction reactions, and then the non-harmful gases come out the other end. So that's one example of a really good use of a catalyst, because it speeds up this reaction with air that's coming in, and then it makes it so when it comes out the other end of your car, you don't give off nearly the noxious gases that wouldn't be nearly as good. All right, the second example is one you learned in the past in your biological career, and these are enzymes, ladies and gentlemen. Enzymes are a very good example of catalyst. There are catalysts all over the place in something called DNA replication, and you all learned about this in the past. So here's my rough, very rough drawing. I'll let you draw it better if you want. So here's my double-stranded, double helix DNA with T's and A's coming across, and our little bases that join together. And then along comes helicase, ending in ASE right here. Anything that ends in ASE, you probably learned in biology class, is a enzyme. Speeds up the breaking apart of the DNA. Primase comes along and gets it ready, another type of enzyme that fits just right to prime it, to get ready to have polymerase come along, another ASE ending, another one that replicates the DNA then. And then remember, this one would be the lagging strand here, and I just love the name of that one, the Ozaki fragment. And then that one, of course, replicates as well with some polymerase, but leaves some little gaps. And then ligase comes along and fills in there and makes sure that that sticks together. So all these that end in A's, ASE right here, those are enzymes. And all those enzymes fit into a specific site to do their job, kind of like a lock fits into a key. And that's a diagram right here for you. Here's the enzyme, and then the enzyme fits right into its little slot, just like the ligase would fit into this little slot, and then cause the chemical reaction to take place. And then what happens is they speed up the reaction, and then they let go, and then they can be reused, which is the beauty of catalysts, is that they don't get used up themselves. Now, I'll let you finish writing this out. And if you want to draw a beautiful double-stranded, double helix DNA, you're more than welcome to, but I want to get a much better picture on here because mine is not very good. So here is my much better picture of the DNA replication, and you can see right here is the helicase coming along to unwind it, primase coming along to get it ready, and then the polymerase, of course, this is the leading strand right here, so it's making new polymer right here. And then we've got the Okazaki fragment right here, and then this one is also getting using polymerase right there, another enzyme, and then we've got the ligase coming in here to fill it in. So you can see that many of the things that you studied in biology, anything that ends in ASE, is always known as a enzyme, and we have enzymes everywhere in biological chemistry that speed up the chemical reaction, and then they can be reused again, which is super important. So I hope you learned a couple things about enzymes, catalysis, catalytic converters today.